All right, so we're going to pick up going over the homework solutions from simple harmonic motion. This will cover really just question 5, which has multiple parts. This is taken from an AP problem. We modified it to add to it so we can cover as much ground as possible. Some of it's pretty straightforward, some of it is fairly subtle. So pay close attention to details and always come back with questions. So what we essentially have is a mass hanging from a spring, that's typical, and we have two different graphs, one of position as a function of time and one as velocity as a function of time, and you see that they're sinusoidal. Okay, so it's pretty straightforward. Okay, so again, we have position and we have velocity as time. Both are sinusoidal. So we're going to have to employ the notes from the third tutorial, where we have to look at what's going on at the beginning so we can understand how to position or how to plot or calculate these positions, velocity as a function of time. So the first ones are pretty straightforward. What's the period, what's frequency, and then what's the value of the spring constant? So how would we get that from these graphs? Well, we won't use the y-axis because that's either position or velocity, but we can see that period or time is along the x-axis for both. So always check that on these graphs because sometimes it could be position. So we see that if we start here at some minimum, we're back at the minimum sometime later, and that's exactly 1 second later. So that's pretty straightforward, 1 second. And we see it repeats itself after 2, etc. If we start here, it's at roughly 0.75, then we're at 1.75, so that's consistent. Frequency, just a reminder of how frequency and period relate. That's 1 over period. So that's also 1, but 1 watt, it's 1 cycle per second. Okay, note that the time is in the denominator. You can call it 1 hertz. It doesn't matter, but something per second. Then lastly, what's the value of the spring constant? Okay, what the heck's the spring constant have to come into play here? Well, we want you to be able to connect that with period or frequency. Okay, in other words, that's the equation where period is 2 pi radical m over k. So you can do the algebra. Right, so we solve for k algebraically, we see that that's going to be equal to, you got to do some cross multiplying and all that. Let's see if I can get that right. This becomes t squared. So that's going to be m divided by, m times 4 pi squared all over t squared. And if we put in the numbers, okay, we should get 4.93 newtons per meter. Okay, so I'll leave that. You should be able to verify that. All right, now where I consider the most difficult stuff, using the equations. All right, so what would be expected position and speed after 4.5 seconds? And we want to do that either by extrapolating, looking for pattern, and then using our equations that we developed in our notes. Okay, so from extrapolation, what do we see? Well, this is at 4.5 seconds, and we see that every half second, right, position-wise, at half it's at position 1, and then it's at position 1 at 1.5, 2.5, so it makes sense that our position is going to be at 1.0. Okay, so since the period is 1 second, and we see at a half second, it's at position 1, and that follows. In terms of calculating this, we want to know what the proper trig function. Remember, our generic equation for x as a function of time is a cosine omega t. But the cosine could actually be assigned depending on what our initial conditions are. So let's look at the graph of position. So what type of trig function do we have here? Well, since at time 0 we have a negative displacement, it's not 0. That tells us it's a cosine, and because it's below 0, it's a negative cosine. So our generic equation we're going to use here is that x is going to equal, now here's the subtle part, it's very easy to make a mistake. We got to take a look at its initial position. I'll come back to that, because look at the graph, it's shifted up, it's not starting at 0, it's shifted here, and it's very easy to overlook that. Plus, now we get the part that we're talking about here, a negative, because we just said it's a negative cosine a, the amplitude cosine omega t. Okay. Now, you got to make sure you're in radian mode when you do this. the amplitude, all right, so let's see if we can work that out. If this is the negative extreme and this is the positive extreme, then it makes sense that, in a sense, this is our 0 position, even though it's 0.75 roughly. So our amplitude is anywhere from the 0 position up or down, so that's 0.25. So if I'm going to do the calculation, I'll talk about the x naught, and then actually I'm going to put in the x naught now, and I'll come back to that. That's 0.75. Okay, plus. So now our negative 0.25, there's our amplitude. Cosine. Now, what's omega? Well, if you recall from kinematics, right, omega is equivalent to 2 pi f, or 2 pi over a period. So f we found is 1, so omega is nothing more than 2 pi. So that's going to be 2 pi times the time in question, and this is after 4.5 seconds. So cosine 2 pi times 4.5. You got to put that all in there. So when I'm in radian mode and I take 2 pi times 4.5 and do the cosine of that, I get -1. I take -1 times -0.25, I get positive 0.25, and I add that to my 0.75, and that's where I get 1.0. Now I want to be clear why this is 0.75. 0.75 is the rest position of the block. In other words, if the block is not stretched, it would be at position 0.75. So that's the initial, and then we add to it what we changed based on the oscillation. Okay, so that can be a little bit complicated. That's probably, of all the problems, the most difficult. But what I want you to recognize is the -a cosine omega t. That should be pretty straightforward. All right, in terms of speed is a little bit more straightforward. Okay, so at 4.5 seconds, look at our speed graph. At the half second, it's at 0. At 1.5, 0. So it stands to reason that at 4.5 seconds, it would also be 0. In terms of a calculation, what do we want to do? Well, we know that our generic equation is v at any time is equal to the maximum speed times some trig function. So what trig function do we have here? Well, that should be pretty clear that that's just a positive sine graph. So that's sine, again, omega t. So that's going to equal, what's our v max? Well, we go up to here, it's roughly 1.5 times the sine. Right, we already learned, or did before, omega is equivalent to 2 pi here because our frequency is f, or excuse me, because our frequency is 1, times 4.5. All right, if you work this out, this whole term is 0. So we get 0, just like we expected. All right, part E. At what time are there acceleration and potential energy at a minimum and a maximum, and then calculate those respectively? Okay, that's a really good problem because neither of the graphs have acceleration or potential energy in it, but we can infer that based on how acceleration and potential relate to each one. So let's tackle acceleration. So which one of these graphs is going to help us with that? Well, it's not going to be position. Position is associated with potential energy, right? The more it's stretched, the more potential energy it has. So let's look at it from a velocity. So what's the connection between velocity and acceleration? Well, that's slope. So if we want a minimum acceleration, we want to know when the slope is minimum for this graph. And when is it minimum? It's when it's flat. In other words, here, here, here. We know that the slope is 0. So what does that correspond to? Well, that's 0.25, then 0.75, right, 1.25, etc. All right, then when will we expect maximum acceleration? Well, when the slope is steepest, and the slope is steepest right here. In other words, when the graph, we don't care necessarily about positive or negative, it's when it crosses over to the 0. Okay, so that's going to be time, I should say times 0. That's when it's accelerating greatest, and then 0.5, 1, etc. Okay, and again, this goes with the idea that we have maximum acceleration when we have minimum velocity. That's a concept we want to repeat again and again. In the previous problem, we have a minimum acceleration when our velocity is maximum. In other words, they're completely out of phase with each other. All right, in terms of calculating maximum acceleration, well, it's not easy to find the slope. You could try to do that, but there's another way we can do it based on the information. And that's really just using the second law of motion. In other words, maximum acceleration occurs when our force is maximum. And when is our force maximum? Our force is, of course, kx. I'm not going to worry about the negative here. But since we want maximum, x is going to be a, the amplitude. So I can say, right, Ka equals ma, the second law of motion. So our little a, max, is going to be k times a all over the mass. Sorry. So we found k up here to be 4.93. You're told somewhere, I can't remember where, what the mass is. And the amplitude, we determined earlier, was 0.25. Okay, again, it's measured from where it's rest. So it's gone up 0.25 or down 0.25. So you plug in the numbers and you get 9.86 meters per second squared. All right, continue on. Potential energy. Whoops. So potential energy is proportional to the distance. All right. Okay, and minimum is when you're at position 0. So, whoops, I don't have enough room on here. So when are we at position 0? We are at position 0. Let's scroll up a little bit more. Stupid mouse. Oh my, I'm going to lose it. Okay, and we got a lot of scribble here, so let me get rid of that. All right, so we're at position 0, at time 0, time, oh, I take that back, at time 0.25, 0.75, etc. So it seems to correspond to what we saw for acceleration, and that is just a coincidence. No, take that back. That's not a coincidence, because when our velocity is at a minimum, acceleration is at a maximum, and our position corresponds with that. Maximum potential energy is going to correspond with this as well. 0.5, it's when we're stretched or compressed the most. And then how do we find that? Well, we could try to do 1/2 Ka squared. That could work. Okay. We could also relate it to maximum potential energies when we're at minimum kinetic energy. Okay, so actually no, I'm just going to do 1/2 Ka squared and plug it in numbers. Again, we have K, A is 0.25, and you work things out, you get 0.16 joules. All right. And lastly, F. Using all the information above, sketch the following graphs as a function of time, acceleration, and potential energy. Okay, so we did all that work, so ultimately we can make a graph from this. And that shouldn't be too difficult because we know when those are going to occur. Okay, so we have an acceleration graph, and we know that minima are occurring right here, 0.75 times. So I'm just going back up all these marks between. We know that our maximum acceleration is around 10, so I'm going to use this line. It's actually 9.86, but let me call it 10. And it goes from maximum, minimum, so we can go like that, come up through 0, go like that. And then always at the odd, or at the half-second mark, we go through that. So not too bad. All right, in terms of potential energy, I'm going to use this. Our maximum is 0.16, we learned. And again, it follows a very similar pattern as before. Okay, at the 0.25 is when we're at a minimum. So actually down here. And then at 0.5, we're back up at a maximum, so it's a little tighter. So I got to drop down to a minimum, go up to a maximum, down to a minimum at the half interval, and you get the idea. Okay, and then 6. Oh gosh, I'm going to have to do that in another tutorial, so I'm going to stop here for now.